Lesson 2, the perpendicular bisector theorem. Here's a little problem that will use that theorem. We've got a new development and we've got two houses picked out. Let's say our two sets of grandparents. One of them is going to live right here and one of them is going to live in this lot. And maybe your parents want to move in the same neighborhood, but they don't want to offend either grandparent. They want to live the same distance from each grandparent. I think the obvious move would be to connect those two houses together and just live wherever the midpoint is, right? So maybe I would choose this lot. Okay, well maybe that lot isn't available. Maybe we're going to have to choose something different. So there must be other houses in this development that are the same distance from both grandparents. Maybe a house right here-ish, or maybe a house maybe right here. Or if we wanted to live out here, maybe on the edge out there. I'm just looking for something that is the same distance to Grandma and Grandpa A as Grandma and Grandpa B. Tick, tick. Well, it turns out that all such possible houses are all located on one straight line. And what do you think is special about that line? Well, if you look at this original segment where the endpoints were at the grandparents' houses, and we definitely picked out the midpoint because that seemed most fair at first. What kind of line hits at a midpoint? What do you call a line that hits at a midpoint? That's called a bisector. Now this isn't just any old bisector because it doesn't go through all slanty or anything. This is a special type of bisector that goes through at a perfect 90-degree angle. And that's the key. If you can find a perpendicular bisector, you know that no matter which house you choose along that perpendicular bisector, that house will be the same distance to both grandparents. And this is the perpendicular bisector theorem. If you find a point that's on the perpendicular bisector, and I can see that this line right here is a perpendicular bisector because it's right in the middle and it's perpendicular. So if you're a point on that line, then if you measure from that point to each of those two endpoints, that would be equidistant. So we see that second set of ticks on there. The converse is also true. If you're a point and you are the same distance to each endpoint of some segment, if I extend this perpendicular bisector, do you suppose it'll hit this point? Or will it just barely miss? Well, this theorem says that if you're equidistant to those two endpoints, then that perpendicular bisector must be going through you. On this first one, do I know that the point is on the perpendicular bisector, or do I know that the point is equidistant to the endpoints? First of all, which point am I looking at? I would be looking at point E, and this is the segment we're looking at with endpoints at F and D. Do I know that that point is on the perpendicular bisector? Or do I know that that point is equidistant to these two endpoints? And I'm going to go with the second one. I know the measurement here is 13 and 13. I know that that point is equidistant to the two endpoints. And so I can conclude that that line I'm seeing is the perpendicular bisector. It's going right through point E. And if it's a perpendicular bisector, then these two little chunks must be equal to each other. That's how I'm going to solve this problem. I know that 5x minus 17 is equal to 3x plus 1. Some fancy algebra, and I found out that x equals 9. Be careful though, because they're asking me for the length of segment DG. That's the 3x plus 1 over here. So 3 times 9 plus 1 is 28. Probably a good idea to plug into the other segment, the FG. 5 times 9 minus 17. 45 minus 17 is also 28. It checks out. And because we started by knowing that that point was equidistant to the endpoints, and then I knew that that line had to be the perpendicular bisector, I was using the converse. Again, make sure you find the answer and identify which of the two theorems you were using. All right, on this second example, Can you see which one is supposed to be the segment and which is the point? This is the segment, segment RL, and I'm talking about point K right here. I'm seeing a little typo on mine. I think they're wanting me to find the length of segment KL, and if it's 4.2 to this point, what would you guess it is to the other point? I would have guessed 4.2, but did you know that there's a little trick on this one? Let's first try to think about which theorem we're using. Do we already know that that point is on the perpendicular bisector? Or do we already know that that point is the same distance from endpoint to endpoint? Well, this time I only know one of the distances from endpoint to endpoint, so it can't be the converse. So it must be the perpendicular bisector theorem. So just to verify, is point K on the perpendicular bisector of segment RL? I almost missed this the first time. I see that it's a bisector, but I don't see the little perpendicular marking anywhere in there. So since I only know that point K is on a bisector, not a perpendicular bisector, then I wouldn't be able to say that this length is also 4.2. So this was kind of a trick question, not enough information. And I guess the setup was leaning more towards the perpendicular bisector theorem. But since we couldn't even get past the if part didn't even come true, we couldn't make a conclusion. So you just be careful when you're doing your problems, make sure that you're looking at a perpendicular bisector, which I think in problem number 1 looks safe because I can see that HB and BN are marked congruent and I see that right angle. So KB is definitely a perpendicular bisector. Go ahead and solve those other 4 and make sure you write down which theorem you were using.